Welcome, everyone. Thank you for joining us. We really appreciate you giving us your time for the next hour or so. You know, LLMs have evolved quickly over the past year, and the promise of automation using these models is coming to fruition. Are you wanting to automate work using large language models? Do you want to be sure that you are taking advantage of the latest advancements for reasoning, planning, orchestration, and tool use? Well, then this talk is for you. We're going to deep dive on those subjects. My name is John Baker. I'm a principal engineer with Amazon Bedrock. I work on agents. And I'm joined by Nicholas Marwell, a member of the technical staff from Anthropic. So what are we going to cover today? Well, we're going to start with what is function calling or tool use? Where did it come from? What are some of the origins of this? How can function calling be combined with the business domain knowledge inside of a powerful model like Anthropic's Claude and really putting that combination together to solve complex problems? We're going to dive into that. We're also Nicholas is going to share some best practices around tool use and calling. Then we're going to explore the question, what are agents and how do they relate to function calling? If you think that's an easy question, what are agents? Wait for that because Nicholas is really going to help us to see the complexity around that and the implications for your project, your agent, depending on how you define what an agent is. And then we're going to dive into some orchestration details, how you orchestrate agents and why that matters, kind of trade-offs you may have to make. And then we're going to combine the business domain knowledge of Claude with the power of an agent to take on an even more complex problem. But before we get started with that, Nicholas, help us understand what's the weather like in London right now.
Amazing. Great to meet everyone and excited to be here. I think I want to start this presentation with a little bit of the why and a motivating example behind tool use and agents. And I want to do that by telling a brief LLM history of answering this question. What is the weather like in London? So in the beginning, there was only text. And if I went to, say, Claude.ai and asked it, what is the weather like in London right now? It might give me an answer saying, I apologize, but I don't have access to real-time weather information. And the reason for this is that Claude knows it needs weather data to answer your question, and it's capable of referencing historical data. It actually might be able to recall for you what the weather was like on June 20th, 1996 in London. But because it doesn't have access to this real-time data and it wasn't trained 5 seconds ago, it doesn't have the information it needs to answer this question accurately. And for a little while, we were stuck on this, and it really limited what models could do. And so we needed a way to let models read from and write to the outside world. And this is where functions, some people call it tool use, some people call it function calling, we'll kind of use these phrases interchangeably in this presentation, began. And the way we did this, and you would never really do this in Claude.ai like this, but I think it's a useful way to kind of start seeing what's going on, is we would tell the model, before we asked it the question from the user, that it had access to a set of tools that it could use when it wanted to answer the question. And so maybe here we've given it access to a get weather tool, an order pizza tool, and a send email tool. And then when we also pass it the user question, Claude is going to look at the tools available, decide if one of them is relevant, or maybe many of them are relevant, and call that tool in an attempt to get the data it needs or perform the action it needs to fulfill the user's request. In this case, get weather London. We then will go and, using traditional software, process this request from the model and return the results. So we may have some get weather function written in Python that we run through with argument London, and then pass back to the model, the weather in London is 47 degrees Fahrenheit. And the model will then take this and realize it now has enough information to answer the user's question and spit back out an answer to the original query. Maybe we don't want it to say according to the get weather tool, and so we can do some prompting to remove that. But this is kind of how we started to resolve this problem of models being able to read from and write to the outside world. And now I want John to talk a little bit about why we want this on a grander scale.
Thank you, Nicholas. Why function calling? Really, let's kind of go through a history of where this comes from. So can an LLM solve a problem like 100 plus 100? Yeah, you've probably said, I've given it much harder problems than that. But then you ask it to do something like count the number of R's in strawberry, right? That's a famous one that went around. It was hard. It was unbelievable that it couldn't really come up with the right answer. So solving 100 plus 100 is the same problem as how many R's are there in strawberry. So let's see where this idea comes from of tool calling. If you trace back to about 2022, you'll find this paper, Miracle Systems, MRKL, Modular Reasoning Knowledge Language, but you generally pronounce it Miracle. And it had a big impact on Gen AI at the time. In fact, if you look at popular agentic software like LangChain, you'll see that they built classes around the ideas in this paper. This class now, I think, has been deprecated, but you'll still find references to this paper in their comments. And so this paper had a big effect on the architecture and the evolving of agents and things like function calling. So what is it that they discovered in this paper or brought to light? Well, they showed two-digit math, very simple math, 10 plus 10. The model could answer this with about 100% accuracy. Three-digit math, like 100 plus 100, it's about 80%. It's about 8 out of 10 times you'd get the right answer. Four-digit math, about 25%. Five-digit math, 9%. And keep in mind, this is all simple arithmetic. They weren't giving it calculus or anything. It was plus, minus, multiplication, division. And they found that with basic five-digit math, less than 1 in 10 was correct. Now, what was going on? Are LLMs just bad at math? Well, no. When they examined the training data for this particular model, they found that most of the math problems it had seen in training were two-digit math. There were a lot of three-digit maths. There was very little four-digit math. There was almost no five-digit math. So when it came to giving the model something that it didn't see very often, it wasn't very accurate in this particular generation of models. And so what did they do? How did they fix the problem? Because they brought it back to nearly 100%, believe it or not. Well, instead of asking the model to solve the problem, tell the model it has a calculator. So it was a prompt similar to this. You have a calculator. Here I'm in the Bedrock console, and I selected Claude Sonnet 3.5. And I just say, use the calculator whenever you have a math problem. And then I want it in this format, calculation, or calculator, operation, operand, operand. And then I give it an example. So then I ask, what is 10 plus 10? And so you see it gives the output. And this brought it to near 100%, even on word problems. Now, no longer did you even have to say, like, what is 10 plus 10? You could say, I have 10 apples. I bought 10 more apples. How many apples do I have? Now, why is it that it got back to near 100%? Well, because the transformer model, which these are based on, has an attention mechanism that makes LLMs extremely good classifiers. They're able to put together the words in the sentence or the operations, able to classify that as a calculator and pick out the operation, parse through and get those operands. Very good at it, highly accurate. So, problem solved, right? Well, you know, whenever we solve one problem, what ends up happening? We create new problems. I heard it over there. Yeah. We've created new problems now. What are those problems? Number one, hallucinations. When you would include examples of, you would say, I have a calculator. Use the calculator when you do this. And the model a lot of times thought it was giving you examples of tools that it had access to. So it started making up new tools that were like a calculator. And so it would hallucinate them. Problem two, prompt injection attacks. Because you were putting everything into the same prompt. You were describing the tools and you were putting the user input right in there in the same thing. The user could then ask questions about the tools and perhaps expose things that you didn't want exposed. The third problem is the verbosity of the input and the output. It resulted in a lot of input tokens, and the latency of LLMs is a function of the input tokens, really. And inconsistent responses led to parsing problems. So when you have to recognize it wants to use a tool versus providing the final answer. Then you need a specific syntax coming out that you can parse. LLMs were not great at that at the time. And so a lot of times it would output a tool, but in natural language, or it would output a final response that looked like a tool. And then it ended up causing your orchestration some problems there. So this is why model providers like Anthropic moved to a special syntax just for tools. I'm going to highlight just a couple of the areas. Now look for these. Nicholas is going to take a deep dive into tool use. Look for these pieces in his deep dive. So a special syntax, it separates the user's question from the system prompt and the tool definition. The model is trained when to use, or to use the tools when provided, so your inputs don't need to be as verbose. And the model provides a stop reason, and it's deterministic. It will say tool use. Nicholas will really show an example of this. And if you depend on that, it's more dependable than trying to parse through the output text. So Nicholas, why don't you take us through a deep dive?
Amazing. So if you're in this room, I assume that you've been building with LLMs a little bit. And I also assume you've started running into issues where maybe you needed the model to read or write to the outside world. Maybe there's some skill deficiency in the model. It's a little better at 5-digit arithmetic now than it once was, but there are many other places where you might want to supplement its knowledge and intelligence. But many of you may have started in the logical place with a package or library that abstracts away the how of tool use. Maybe this is the tool use API on Anthropic. Maybe it's Bedrock agents or LangChain. And what I want to do for the next few minutes is peel back this layer of abstraction and show you what's going on under the hood. Because I think when I do this, you will realize A, it's simpler than you think, and B, you'll understand why it is important to do things like write great specs for your tools in the same way that you would write great documentation for your developers. So this is what tool use actually looks like. Yeah, this is a good take a picture of it slide. It's actually quite simple. We start by describing for the model in a prompt a function calling syntax that it should follow and a set of available functions or tools that it has access to. We then combine this in the same prompt with a user message or whatever the thing we want the model to go try to do is. We pass these to the model and generate a completion. And then we take that model's completion and we do a check to see if it contains a function call. If it does, we parse out which function call or calls the model is making, and we execute them, client side, server side, wherever it may be, with traditional software. Once we've done that, we're going to pass the results of that traditional software back to the model, along with all of the information we gave it in the prior prompt. And we're going to let the model generate another response. And we're going to repeat this until the model doesn't make a function call, which we will take to mean that it's done, and it has an answer to the task we asked it to do. And then we can take that final task, we can hide all of the tool use it was doing behind the scenes from our user, and we can return the user just the final conclusion of the model, or if we want to, the process we used along the way. Maybe we want the user to be able to come in and audit what's going on. So let's look at each of these steps a little more closely. How do these actually work in your prompt and in your code? So the first thing I said we need is we need a function calling syntax and some available functions. I'm showing a very simple example here. The function calling syntax might look something like, in this environment, you have access to a set of functions defined in functions tags. You call functions using the following syntax, and then here I show an XML syntax, but you could really use several different things to make this work. You also have access to the following functions. And in this case, I only show one, but Claude is now capable of handling dozens, if not hundreds, of these tools at once, and I'll talk more about that later. And here I've used kind of a JSON spec to describe the function, but again, you just need to use a spec that you think is easily interpretable to the model. JSON's a good start. Then we need a user message. Well, I'm going to show an example that's relevant to the tool that I showed so we can actually use it. Maybe we'll have a user message like, I'm in Austin. Do I need a coat today? Well, how could the model make this judgment without first knowing what the weather is? We're going to see why it needs to answer this soon. And so we've collected this all. If many of you have probably called a completions API before, you can have a system message and a user message. We compile this in our kind of message list. And then the next step is to generate a model response from them. Here's what our model response is probably going to look like when we ask this question. It's putting out the syntax we described it should use for the tool, function call for each individual one, the name of the function it wants to call, the parameters it wants to pass, in this case, city, Austin, and state, Texas. And really importantly to note here, what you don't see, but John mentioned earlier, is we're adding an additional stop sequence parameter to our call to Claude. So when you normally call a language model in one of these completions APIs, there is a default set of stop sequences that the models have been trained on to know when we should stop generating tokens and return you something. But you're actually allowed to add any additional stop sequences you want. And we take advantage of this in tool use. Because we know the syntax of tool calling, can know that there is a specific token the model is going to output whenever it's done. And we can stop it right after it outputs that token. Why might we want to do that? Well, there's like maybe an okay reason of trying to save some tokens or something, but there's one that's much more important, which is models are next token prediction machines. And if you let them keep going after they finish writing their function calls, well, the thing they expect to see next is an answer or a response from calling that function. And a model will actually just make up an answer if you let it keep going from here. It's actually, if you ever want to simulate results to some function, a great way to go about doing that. But so we need to use this stop sequence, or the model won't stop at its function call. It will continue on, make up a result to that function, and then give the user an answer. And so we've stopped it, and now we need to do our check. Here's a really simple snippet of Python code that checks if our answer from the Claude API contains this function calling syntax. We check if the stop reason is a stop sequence, and if the stop sequence is the expected end function call sequence. And if it is, we know with near certainty that this does contain a function call. And so right now it did, we just saw. And so we're in this yes track of the diagram. And the next thing we need to do is parse out the function call that Claude is trying to make, or calls that Claude is trying to make, and execute in software. I'm going to skip the parsing bit for brevity. That's usually a bit longer. But here's what the execution bit might look like. We probably wrote some Python function called getWeather. It takes in the same parameter as we told Claude it would take. And maybe it calls some weather API.currentWeather and returns a natural language phrased answer to the function that Claude called. You don't have to do this, but we often find that returning function results in natural language helps the model better understand the results it's seeing. So here, we're not just returning the current weather, we're returning a kind of interpolated string. The current temperature is weather.currentTemp. There is a weather.precipitation chance of rain today. So what's the next thing we do? We take these results and we show them to the model. But importantly, we need to show it to the model with all of the prior context of what the model was trying to do. If we just gave it these results with no context, it wouldn't really know what to do with them. And so we're actually going to be continuing the chat conversation from before. We still have our system message with our function calling syntax and available functions. We have our user message, what's the weather in Austin? And we have our assistant message that has been extended. And this is an important footgun that you need to look out for. One thing you might consider doing is passing the function results as a new user message. The assistant asks for a function, the user gives it back. But what we've found is it is much, much more effective to actually pass these as a continuation of the assistant message where the function was called. And this is a cool trick that you can do with Claude, where if your messages list ends with a user message, we will automatically start a new assistant message in the response. But if your messages list ends with an assistant message, instead of starting a new user message or a new assistant message, we will just continue sampling from where that assistant message leaves off. And so we're going to continue sampling the same assistant turn of this conversation where Claude has called a function and gotten back the results. OK, what do we do now? We sample. We get a model response. And maybe this time the model has the information it needs in order to give a good answer. And so it might say something like, it's 30 degrees Celsius in Austin today, and there's a 5% chance of rain. No need for a coat of any kind unless you want to be extra careful with the rain. We're back here. We're going to check if it contains a function call. We're going to use this same little code snippet from before. And this time, it didn't call a function. It gave us an actual answer. And we can take this as an indication that the model is done, and it's ready to return some set of results to the user. And so we would take this and presumably show that text to our user. All right, so that's a how does it work? And I'm going to pass it back to John to talk a little more about using it.
OK, fantastic. So we've seen some of the origins of function calling. We've seen a bit of a deep dive on how to make use of it, some of the best practices. Now let's combine the power of the model's pre-training and training, its knowledge of the language and even of the business domain, and let's combine that with function calling and do something really cool. So we know as software developers, domain knowledge is more important even than knowing a particular technology. Knowing about your business helps you to be more productive. Almost every experienced software engineer will explain that same thing. It helps you to communicate with the business. You know some of the implied requirements, right? So let's imagine that we're a new software developer at a financial firm. Our first ramp-up task, first day, something easy. You're asked to display the percentage return for any stock symbol given. You're given a price tool, and what that does is you give it a date range and stock symbol. Now, what comes out of it is a list of open, high, low, close prices. So the manager says, OK, go on, and you say, OK, I can do this. That seems pretty simple. I know percentages, right? Well, there's some implied requirements. For instance, how do you calculate a percentage return of a price series that has open, high, low, close for each day? So what do I mean by that? Well, if I use the open to the close, I kind of get one number, right? If I do low to high, I get a different one. If I do open to open from the beginning of the day to the open maybe the next day, get a different one. And close to close. So how do I do it? And you know, this is my first day. And I know you're not like this, but I am. Sometimes when I'm new at something, I'm afraid to ask. So here's our first day. I'm afraid to ask because I'm shy. I know you can probably tell that I'm shy. So I really kind of wonder, does it even matter? Maybe I could just randomly choose one of these because my manager won't know anyway. It'll just be a percentage return. But you know, if you think about it, it's kind of a simple thing, but every day you turn on the financial news, they'll show you a percentage return. They'll say, the S&P returned such and such for today. They never explain how they get that percentage return, right? So we all must understand it. Well, let's see. How do I calculate the percentage return for October 14th on the S&P 500? If I use open to close, I get about 0.5%. If I use open to open, I get about double that. 0.95%. If I use close to close, again, it's near that 1.5 times it. Those are drastically different. And you know, on this day, it switches from positive to negative depending on which one you use. So when I look at that, I say, yeah, it might matter. My manager might catch me. Okay, but I really want to do a good job here. So you know what? I'm going to see what Claude does. I'm going to use the Amazon Bedrock Converse API, which puts in a lot of those best practices for you. It does the stop token, and it standardizes that tool use syntax. So I'm going to use that and choose the premier model, and I'm going to say you are a software developer at a financial firm, and I am going to say you have a calculator. And then I am going to just go ahead and pass in the data that I had pulled up in the price tool. And then I'm going to ask, what is the percentage return for each day? And I get this exact output from Claude. To calculate the percentage return for the past 5 days, we need to use the closing prices. The closing prices, not open to close. So what it does is it pulls out all those prices, and then it tells us to use the tool. It starts out with the minus, and then it does the division, and it pulled out the right 2 days. So we're left with the question, though, because it's our first day, why? We want that business domain knowledge. Is there a business reason why it is the close of day 1 to the close of day 2? Or did Claude just randomly choose one? Is there an implied requirement? Well, let's ask Claude. Why should I measure a financial instrument's percentage change from close to close rather than open to close? It gives several reasons. I want you to zoom in on 2. Number 1, consistency. Closing prices are considered more reliable as they represent the final agreed upon value. They are set by the exchange in most cases. In legal terms, it's called mark-to-market. GAAP accounting also requires that type of price to value an instrument. So these are legal prices, usually the close price for the day. It's published by the exchange. Data completeness, we want to take in that overnight volatility. A lot of instruments trade overnight in a pre-market in the morning. If you do open to close, you will miss that. So Claude knew it, right? Now, we're kind of left with the question, we saw some power with function calling. Saw Nicholas demonstrate how to write an orchestrator loop yourself. If this is so powerful, then what are agents?
Well, about a year ago, when I started working on the agents thing, I asked myself this question. I thought I had a pretty good answer. I'll share maybe what my answer at the time was in a bit. And then I started going out and talking to some of the earliest customers who were trying to adopt agents. And I very quickly learned that not only was my answer not the same as theirs, but their answers were not the same as each other's. And this term had become overloaded to the point that nobody could really agree, and still can't agree, on what an agent is. And so while I wish I could just put up a nice definition for you all on the next slide, it turns out instead I have to put up something like this. We use this to resolve the is a hot dog a sandwich internet flame war. I figure it can resolve the what is an agent one, no problem. And I now think about agents on these kind of 2 axes. We have an axis of agency, and we have an axis of effect. The agency axis is about choice. How much are we letting the model make its own decisions about what to do, when to do it, when to stop and give an answer, and what to show to the end user or end customer of its outputs. On the other axis, we have the effect. And this is really what is the impact of what the model's doing. This is where tool use comes into play. A purist would say that something is only an agent if it can both read and write from the outside world. A radical might actually say, doesn't matter. Effect is not important to an agent. And so you end up with some folks who would tell you any response from a model is an agent, and some folks that would tell you you have to be something bordering on like a virtual employee in order to be considered an AI agent. So let's see what this looks like on that chart we just described. Here we have like maybe the version of this chart if you are an effect and agency radical. And this is just like any language model completion is an agent. It doesn't have to do any tool use. It can be a single step. You can be incredibly prescriptive with the model about what it has to do, et cetera. This is most of what we see deployed out in the market today that I think fits with my definition of an agent. This is the effect purist agency neutral. And what this is something where we need to be doing some level of tool use. It doesn't have to be read and write, we need to be doing some read and write tool use. And we need to let the model have some agency in its decisions, but it doesn't need to be given the full level of autonomy we might give to a human. And why is this flow agency neutral and not agency pure? Well, we're actually governing and constricting the model's autonomy a lot with each of these kind of pink boxes. We have a user message, and before we let the model take a look at it, we actually run some other classifier over that message to decide what prompt should we give to Claude, what tools should it have, what types of instructions should be in the prompt. We're immediately kind of constricting its space of options and its set of instructions for it. Then we let the model do a bunch of very agentic feeling things. It can do some tool use, it can come up with some answers. But before we show it to the customer, maybe we want a human operator to check what it's going to show. And so we have yet another control point on the model's autonomy that it is not entirely in control of. This is for kind of the most, people building the most cutting edge agents in the market today, what you often see from folks. And then funnily enough, if we go to that top left corner, the true agentic purist, we kind of just end up back at the tool use chart. Tools in a loop where the model gets to decide what to do, when to do it, and perhaps most importantly, when it's done, how many steps it needs to take. That is kind of the agent purist. And so in a funny way, the original conception of tool use was actually the agent conception of tool use to people who have the strictest definitions of what makes an agent an agent. But why should we care about this like change from tool use to agents? I think what I'm seeing, and I have been constantly surprised, I think like humans are bad at knowing when we're on exponentials early in the exponential, is that models are rapidly expanding the number of tools that they can handle at once and the complexity and time horizon of the tasks that they can take on. Previously, not that long ago, less than a year ago, Claude could reliably take actions when given maybe a limited set of tools, 1 to 6 at most, and a narrow, short time horizon task. If we were in advertising, we might say something like, Claude, what is the CTR of my ad campaign? That's going to require Claude to basically maybe make a single tool call to look up the relevant data and then do some computation. Today, we are already seeing that Claude can reliably take actions when given a large set of tools, dozens of tools. I've even seen a few instances of hundreds of tools, and a complex but short time horizon task. Claude, can you prepare a full report on the current state of our advertising budget? But in the future, as these capabilities keep expanding, we expect that Claude is going to be able to reliably take actions when given not just a large set of tools and a complex task, but a task that is medium to long in time horizon, something that may take dozens or hundreds of steps to complete and will be less atomic in its units of work. Claude, can you analyze our last year worth of data, suggest a new advertising campaign strategy based on that data, and launch it? This is many people doing many steps and units of work in a traditional operation today. But don't just take my like hypotheticals on a slide for it that this progress is happening. Take some actual data. So one agentic use case that is probably one of the two most watched in the world today is coding. Agentic coding is a little different from maybe the code completions that we had a few years ago, where you're writing a line of code and a model maybe writes the last 2 tokens of your line of code. Agentic coding is when we give the model a task and maybe a code base and ask it to just submit a pull request or something like this. So we have an internal benchmark for agentic coding. There are also lots of great external benchmarks. But on our internal benchmark, Claude is given an open source code base and a natural language request to write a feature or fix a bug. And these are actually requests that were opened in real life against these open source code bases. You can see in like the GitHub tickets. Claude's job then is, without any human intervention, to implement changes to the code base, and we select issues where those changes require searching, viewing, and editing at least 3 files, and go all the way up to 20 files in some cases. Importantly, Claude is not just able to write some code and be done. It's able to write but also run code in a sandbox as it makes changes, to test the changes it's making and understand whether it's achieving the task before telling us that it thinks it's done it. So if it makes a mistake or it's uncertain whether something will work, it can try it out and resolve it for itself, much like a developer would do before opening the pull request for someone else to review. Claude is then evaluated on whether the tests for the code base actually pass for this change. So when we released Claude 3, less than a year ago, we released Claude 3 Haiku, Sonnet, and Opus. And this is kind of in increasing order of model size and intelligence. And at the time, Claude 3 Sonnet was scoring about 21% on this task. And Claude 3 Opus, which is much larger and more capable than Claude 3 Sonnet, was scoring maybe 38%. Less than 6 months later, we released the first model upgrade for this family, which was an upgrade to Sonnet. And Claude 3.5 Sonnet went from scoring 21% on this task to scoring 64% on this internal benchmark. That was 3 times or so better than its prior generation, and nearly twice as good as a model much larger than it from only 6 months or less ago. And so the progress is not just in observation or in vibes, but we're actually seeing it on benchmarks that we care about and we feel represent real-world applications of the model. And with that, I want to hand it back to John to talk a little more about Bedrock and agents and function calling.
Well, thank you. So we've been through quite a bit here. Let me get a drink real quick. This dry air really gets to me. Okay, so Bedrock Agents allows you to make use of all of these things that we're talking about. And I'm showing you right now on this slide the internal architecture of Bedrock Agents. It is top secret right here. So agents can make use of tools that you provide with lambdas, or we support something called return of control, where you can just host it locally and we'll tell you when to invoke the tool. So you provide the function signatures, the description, the parameters. You can also use knowledge bases. We go ahead and do the prompt engineering for you if you configure a knowledge base, and we'll go ahead and configure that as a tool as well. And so when you give it a request, we use the Converse API, and we send that request to the model along with the proper tool blocks, and we'll do the prompt engineering for you. And then the tool use response comes back, we'll execute the tools, or if you use return of control, we will tell you go ahead and execute it. So how does this work internally? So let's go ahead and dive a little bit deeper. Agents, Bedrock agents, by default, use a REACT strategy. REACT stands for reason and action, and it's very much exactly what Nicholas showed there, where what we do is we will take the user request, the orchestrator there refers to our internal code, and we'll take the user's request, we'll build a Converse API request with the tools that you provided, and we'll send that to the model you selected. And then what happens is it'll tell us which action to do. We'll execute the action, and then we will combine the request, the original request, the tools, and the result, and we will keep doing this until we get a final answer, in which case we send that back as the invoke agent API. Now, React has some advantages as an orchestrator style and a prompt style. So usually when you see React, you'll see the term maybe orchestrator or prompt style. That's kind of what we refer to these as. And some of the advantages is that at each action, the model is going to make a decision on what the next step is. So it develops a plan, and then you'll even see it. It'll output the plan, and then based on the action, it'll decide what's the next action. It may modify the plan along the way. So it tends to be highly accurate and resilient in comparison to some of the other prompt styles. So it works naturally with tool use. Most of the model vendors train for React style prompts, a chain of thought style prompts as well. So the disadvantages to this approach, number one is latency. Because if you have two model calls, you have two tool calls, you have 3 model calls. And a lot of times those model calls can take 6 to 10 seconds. So 2, 3, 4 tool calls, you're easily getting up to maybe a minute worth of latency. It tends on longer trajectories or longer plans, it may forget the plan over time. That's kind of what he was talking about, the complex time horizons. It's also difficult in a React loop to follow a predefined plan. You may say, I just want it to do these 5 steps, and you'll input that, and you'll see that it doesn't always do that. And you'll say, why? I told it to do these 5 steps. Because React is made to let the model establish the plan. So there are other orchestration types. For instance, reason without observation, or ReWU is one. The way this works is you send your request and your tools, but it's a little bit more verbose of a prompt where you're going to tell it that you want it to output all the steps at once. Don't give me the next step, give me every step at once. And now what it does is it gives you the entire plan of actions, and you go off and execute that sequence of actions. And then optionally, you can send back the result, and in which case it'll give you a natural language response. So with ReWU, the advantage really is latency. You can, if you have 4 tools that need to be invoked, you can do that with just one model call. It can tell you which tools to actually use. It's very good at following a plan, but the trade-off is that you actually end up writing quite a bit of code to parse these tool executions out of the model's response, because you need, if there's dependencies going from one tool's output to another tool input, you need to do that yourself. In React, the model takes care of that kind of dependency. Here, you will have to do it yourself. So a little bit more code, and it's a little bit more brittle. React, you will find that because you write less code, the prompt is a little less verbose, that you will just take advantage of model upgrades. They get better over time. With something like ReWU, it's a little bit more brittle on new model upgrades. You may find that you have to go back and do the prompt engineering. So I said the default orchestrator for agents is React. You can do ReWU as well, or you can do any orchestration type. This was just announced on Friday, and we have a blog post up there, Getting Started with Amazon Bedrock Custom Orchestrator. We have an example of ReWU that you can use today and compare it against the default React and see which one is better. It's custom. You put it into a Lambda. You can just take our code, put it into your Lambda, run it with an agent, and if you want to redefine the prompt, you want to do it any way, you can do that. And so I encourage you to read the blog post, because we go deep dive into React and the plan and solve type prompts like ReWU. So you can do any orchestration style now. So now let's take a look at a more complex example with an agent than what we had with our function calling. So we want to take advantage again of the model's business domain knowledge with our agent, and we're still a new software developer at a financial firm. It's still the same day. And you know what the problem with solving problems is? We already said it. Now you have new problems, right? So you showed your manager, and they said, wow, you really know this stuff, even though you're just a brand new hire, so I'm going to give you something significantly more difficult. We were able to figure out calculating percentage change. Now we get a more complex task. We're asked, calculate the annualized volatility of the S&P 500 based on the past 30 days. Oh no, now we say this sounds complicated, but again, first day on the job, I want to impress the manager. Maybe they'll give me a raise on the second day. We have some questions. Number one, what is volatility? Number two, what is the industry standard method for calculating it? Number three, what data will I need? So we go ahead and we just ask Claude, right? We'll just ask, what is volatility? What is volatility in financial markets? So it outputs several things. Let me highlight them for you. The first key, volatility in financial market refers to the degree of variation or fluctuation in the price over time. So if we have 15% volatility, we could say, okay, we could expect to gain or lose 15%, or it could go up 8% and then down 7%, something like that. Again, this legal is going to make me say this. This is not financial advice, okay? But basically, that's what volatility is. How do you measure it? Well, it's the standard deviation. Oh, okay, well, we remember that from school. Standard deviation, higher standard deviation is higher volatility. Standard deviation, I think the formal definition is the average distance from the mean. So the third key here is historical volatility. They said based on the past 30 days, so we're doing historical volatility rather than future-looking implied volatility. Okay, so now we kind of write down our requirements. We need 30 days of data. We're going to have to calculate the percentage change. We want to take the standard deviation of the series. That gives us the daily standard deviation for the past 30 days. But wait a second. They asked for what would be the annual volatility. We're going to end up with the daily volatility. So how in the world do I convert daily volatility to what it would be in a year, what I could expect over the course of a year? Well, you know what? Let's see. I go ahead and I go build an agent, and rather than giving it a simple calculator, this time I'm going to check the box in Bedrock agent. When I create the agent, I'm going to say, go ahead and give me a code interpreter. Code interpreter is a sandbox execution of a Python REPL, and when Claude generates code, it will execute that code for you and give you the output. So we do the prompt engineering for you. You just turn it on, and then we also sandbox the environment for you and manage the session. We're going to give it a real market data tool, and that way it can query it. And so what I did was I built a little demo here with a simple UI. I'm going to go ahead and play this, but what it's going to do is I'm going to input the question, and you're going to see kind of the trace events fly by. So the trace events in agents are the intermediate events. It's telling you what tool it's using, when it's invoking the model, when it's getting a response from the model, and then you'll see it'll generate code, everything. So let's let it fly and see how it does.
I've created a Bedrock agent. This agent has access to two tools, a code interpreter and a price tool. The price tool can query stock prices given a symbol and a date range, and the code interpreter will execute code that's given to it. So if the model generates Python code, the code interpreter will then execute it. Let's see a complex problem being solved here using a combination of the model's business domain knowledge as well as these tools. Let's see how the agent solves this. Okay, so we see that it's arrived at the final answer. And on our screen here, we saw all the traces come flying by. Bedrock Agents outputs trace events, which tells us all the intermediate steps being done. So we'll be able to find in these trace events the data tool or the price tool being called. We'll also be able to see the code interpreter being called and what code was generated to arrive at this answer of 13.07% for the annualized volatility. So let's go down and let's see if we can find where it queried the data. Here we see the price tool being invoked, and it's doing so with the parameters symbol of SPY, the from date 10/15/2024, and the to date of 11/14/2024. And this is the date today, 11/14/2024. So let's see, once it got this data, how it made use of it. Okay, so we can see the data that was injected into the code. It chose to just, since it was just 30 days, it just chose to go ahead and put it in as a constant. And it generated this code here to calculate the log returns. Remember when we talked about function calling, to determine the percentage changes each day, you do close to close. So it knew to do that. And now it takes those log returns and takes the standard deviation that gives us the daily volatility. And since our original question was for annualized volatility, it knows that to scale that volatility to a yearly number, it has to do so by the square root of time. 252 is about the number of business days in a year. So it took 252, took the square root, and it scaled the standard deviation by multiplying it and produced the annualized volatility. And that gave us our final answer for the annualized volatility for SPY over the previous 30 days is, and it came out to about 13%. So we see how the agent combined the use of tools with the business domain knowledge that Claude has learned from its training process.
Okay, very good. So we see how it was able to solve the problem, and it knew to use the square root of the number of days in a year. So what's interesting is exploring in your business domain through prompt engineering, playing around with the console, what kind of knowledge Claude has about your business processes, or even the standard practices within your business domain that are industry standard practices. So explore that. So what does all this mean for you? Well, agent orchestration and prompt style can be specific to your problem, like plan, execute, and solve, or rewoo was an example of that, or it can be very generic, like React. When do you want to be more specific versus more generic? Kind of the agent purist or functional purist or functional radical? Like when do you want to be, well, if you have a specific plan to be followed or you have hard latency requirements, then maybe plan, execute, and solve like rewoo is a good choice. If you have asynchronous processing, you want to be resilient to things that might happen with the tools that you use, then React might be a better choice. If you want less freedom to change the plan, then rewoo or plan and solve. And so these are some of the trade-offs you have to make. Another thing that you may have noticed is that I was using very generic tools, calculator, code interpreter. You could extend this out to maybe S3 or databases. So should you make your tools very generic, like just give it access to the S3 bucket, just give it access to the database with text to SQL? Should you give it a code interpreter? Should you make these very specific? I could have created a percentage change tool. I could have created a volatility tool or a data API tool. So when do you want to do one versus the other? Well, if you do very generic tools, you give the model more freedom, and it can handle a lot more use cases, but it may tend to be a little less accurate. If you give it very specific tools, you're going to kind of limit the use cases that it can handle, your agent can handle, but you may see a trade-off that it's a little bit more accurate. So those are some of the things you have to test. So in conclusion, function calling is a powerful construct supported by advanced models like Claude, which can utilize tools and the business domain knowledge to solve complex problems using now a standardized syntax. Agents builds on top of function calling to provide planning and orchestration, solve more complex problems, providing automation of work using generative AI models on Amazon Bedrock. If you want to find out more, I've got some blogs and things that you can go to here. So if you missed any of the slides, you say, oh, I really wish I would have taken some more pictures of the slides. They will put this talk on YouTube. So feel free to look them up there. And we really, really appreciate you giving us your time. And so thank you very much. Please complete the session survey. If you want to connect with me or Nicholas on LinkedIn, feel free.